start the recording. That's generally a good idea. All right. So let's go ahead and talk about the Biot-Savart law. And so what exactly is the Biot-Savart law? Or at least what are you guys seeing in this class? Because technically you guys only mess with a simplified version of it. Actually, it doesn't give you the full Biot-Savart law in your formula sheet, but he gives you the simplified version for what you guys need. Well, the Biot-Savart law, at least for what you all are seeing in this class. Go ahead, Zach. I see you're typing. How's it going, Derege? Talking about the Biot-Savart law right now. And what exactly is it? Equation of B is equal to mu naught I over 2 pi r. And what exactly does that mean? What is B? What is I? What is the context of this? We're assuming mu naught is the constant. I is generally a current, right? So what is the current and what is this magnetic field? Is it the magnetic field a certain distance away from a straight line current? And what specifically about the current what's special about the current? Exactly. It has to be essentially an infinitely long wire, an infinitely long line of current. And so what about the magnetic field B? So here we have mu naught I over 2 pi r. That's our magnitude. That's the magnitude of our magnetic field, right? You're welcome, David.
Oh, welcome.
So we're talking about the Biot-Savart law. And so we have B mu naught I over 2 pi r, infinite line. And what about the direction of B? So if we have our current coming along like this, what's the direction what is B going to look like? Is it just radially outward from the current? Is it radially inward? What's going on?
Sorry about that.
No problem. So out and perpendicular. So you're right. It's out and it is perpendicular. And how do we actually find the direction of our magnetic field?
purpose. So we're trying to find the direction of the magnetic field.
Yep. So we're
So so your thumb would be pointing to the way of the current. So your magnetic field, on the left part of it, it would be going into the page, and then on the right part of it, it would go out of the page.
well. I'm sort of just, but
Oh, yeah.
you got the idea of thumb points, fingers curl in the direction of the magnetic field. This is sort of hard to visualize in 2D. But I'm sort of imagining the current is like coming out of the page slightly downward.
It's like a little circle. It's like spinning through. Yeah, like that.
Exactly. So we have the magnetic field is always going to be perpendicular going around the current based on the direction that our fingers curl, with our thumb in the direction of the current. And so this is basically all you guys need to know about the Biot-Savart law, even though this isn't actually the Biot-Savart law. Fun fact. If we go ahead and Google Biot-Savart law, just go to images because there's like a nice image. We have this BS. This is why it's the BS law. We have the infinitesimal magnetic field is equal to mu naught I times dl cross product with the radial direction over 4 pi r squared. Does anyone want to go ahead and solve that? For example, derive it for an infinite line. Yeah, exactly. Screw this. This is dumb. So essentially,
just use like a lot of calculus.
Yeah, it's honest. It's not too bad in all honesty.
I forgot what it was called, but I think you have to use the left hand or one of the rules. It's like one of the lined rules where you have to add up. Or it's not midpoint. No, it wasn't midpoint. I'm trying to think what rule. It was you have left endpoint, right endpoint, you have midpoint. I forgot what that one rule was. I think that's how you add it up, because you have to add up all your lines, and I think you have to use the midpoint rule, or one of those rules. It's not too bad, but it just looks daunting.
Essentially, we just set up an integral, and we have to integrate over the length of our wire for an infinitely long wire. We're integrating from negative infinity to infinity, and it ends up being, we have this cross product, which turns into, what's the cross product? If we want to find the magnitude of a cross product. Example, A cross B is equal to what? It's going to be...
Just the directions? Isn't it the direction?
No, I'm talking about the magnitude of A cross B.
Oh, the magnitude?
Yeah.
Wouldn't be A times B?
Times... Yeah, Alana's got it. A times B times the sine of theta. So the magnitude of A times magnitude B times the sine of the theta. And in this case, and we would essentially set up as an annoying integral, integrate from negative infinity to infinity with our cross product, where it's this is our point and this is our angle theta. It gets so essentially the angle theta would be in reference to if this is the point we want to find the magnetic field at, and this is our line, and like this is our arbitrary point that we're at, that we're integrating at. Let's say the current's straight upward. Then we have ds, which is the segment of the current, and then r is the radial direction, which is this. So this here would be our angle theta. And it's sort of annoying, but the sine theta, we could set up a right triangle, and SOHCAHTOA, sine is opposite, so it would be r over L. Integrate from negative infinity to infinity. Who cares? You guys don't have to do that for this class. You end up getting this. that's all you guys need to know. I figured it'd be interesting for you guys to at least know where it comes from. But so we can use this, simplified version of the Biot-Savart law, which this gives you the magnitude of the magnetic field, and we use our right-hand rule to find the direction, and you guys can pretty much solve any problem involving magnetic fields and wires. Does anyone have any questions about this so far? Would R be the hypotenuse of that triangle? Yes, it would be. Yep, so if this is the direction here, R is our length from our point to the point the point on the line to the point in space. So this is R, and that's why this direction here was the R hat. But don't worry about this unless you eventually end up taking Physics 407. And even then, I'm taking 407 right now, and I haven't seen anything with about Savart law yet. All right, so let's go ahead and hop into an example. So we're going to have an infinitely long wire with current I0 3 amps to the right. And it's going to be placed along the x-axis. So it's going to look something like this. Boom. Very long, infinite wire. And then another 5-meter long wire placed right above it. And this wire is a finite length. So we have I0, and then we have another wire sitting above it. So what's going to be the magnetic field distance r away from I0? And then what direction is the magnetic field going to be in above and below I0? Let's go ahead and just take 2 minutes, and then we'll talk about it. So what's the magnitude of the magnetic field? And then what direction is it in, both above and below I0? Ignore this wire for now. Also, if everyone hasn't already, if you could fill out the attendance form that's in the announcements channel, or also in session text, if you could do that, that'd be greatly appreciated. Thank you. All right. So, what's going to be our magnetic field at any distance r away from I0? How do we find that magnetic field? Remember what we just talked about? It's just the Biot-Savart law, right? It's just mu naught I over 2 pi r. And so what direction is that going to be in? What direction is our magnetic field going to be in, let's say, above I0?
Above above I naught. So 1 second. Above I naught, it's gonna be out of the page,
Exactly.
and below I naught, it's gonna be into the page.
Yep. Exactly. And you got that by using the right hand rule.
Yeah, just
Yep.
curling my fingers.
Thumb to the right, curl your fingers around. You'll see above the wire, your fingers are coming towards you. Below the wire, they're curling away from you. And so, what direction is the force on the upper wire going to be in if the current is running parallel to I naught? So let's say we have a current up here, I1, running parallel. And then also, what direction would it be in if the current was running anti-parallel? So in the opposite direction of I naught. Let's take like 4 minutes and we'll talk about it. So what direction would the force on the upper wire be if the current was running parallel and also anti-parallel? So, how would we actually go ahead and orient the wire so that there's no magnetic force acting on it? What's one way we could into or out of the screen? Exactly. And why is that? Can't contort your hand that way. The simpler explanation that doesn't involve any hand contorting or breaking. So we know our magnetic field is out of the page, right? So, and how do we calculate the magnetic force on how do we calculate the magnetic force on the wire? What's the formula again? F equals IL cross B, right?
Yeah.
And what's the cross product again? What if we want to find the magnitude of a cross product?
Wouldn't it just be the AB sine theta?
Yep, exactly. A cross B is equal to AB sine theta. Yep, so ILB sine theta. L cross B becomes L times B times the sine of theta. And if we want that to be 0, we can make the sine of theta be 0, or in that case, theta would have to be either 0, which means it's coming out of the page, or 180 degrees going into the page. Nice and simple. So now, let's say we want to find the force acting on the wire, or we have the force acting on the wire, and it's 10 newtons straight upward. What would be the magnitude and direction of the current? How do we actually find that? So, we know that the force is equal to ILB sine theta. And let's just say sine of theta, say theta is 90 degrees, so sine of theta is 1. And we're given the force. And we want to find the current, right? Well, first of all, let's also plug in what we know for the magnetic field. We know it's mu naught times I naught over 2 pi r. So we can just plug that in. So we have mu naught I naught L over 2 pi r. We have r, it's 1 meter. We have the length of the wire, it's 5 meters. We have our force, 10 newtons. We have our I naught. Now we just need to solve for I. So I is equal to 2 pi r F over mu naught I naught L. And if we plug everything in, we have 2 times pi times our 1 meter times our force, which is 10 newtons, divided by, what's the value of mu naught? It's a constant.
4 pi times 10 to the negative 7.
Yep, exactly. 4 pi times 10 to the negative 7 times our length of 5 meters times our current of 3 amps. Ooh, gotta separate this. There we go. And we get a current flowing in the upper wire of about 3.3 times 10 to the 6, so 3.3 mega amps, which is really strong current. So essentially, I mean, it's something you should probably notice, but because our current has a constant, a factor of 10 to the minus 7, generally these forces acting between wires is relatively small. Does anyone have any questions about this so far?
No.
All right. So, let's go ahead and hop into the next example here. So we're going to have a loop of wire with a radius of 3 centimeters and a clockwise current of 3 amps is going to be placed surrounding the origin in the XY plane. Essentially what that means is if we have our XY plane, what direction would the Z direction be in this case, if we have X and Y? How would we find the direction, the Z direction? Because normally we have, whatever, we might have like Z defined as straight upward. And we have X, Y. How do we relate them? I don't know if you guys have covered this, but maybe you'll notice it. He's going out of the screen. And how did you find that? Oh, you just rotated the axis. That's fine. But the way we would relate them is actually another right-hand rule. We point our pointer finger in the direction of X, our palm, so our middle finger curls upward in the direction of Y, our thumb points out of the page. Just fun fact. Another right-hand rule to add to the about 20,000 of them you need to know. But so we have our loop of wire, radius 3 centimeters, clockwise current 3 amps, so it's going around like that. We'll call it I naught. And so what would be the magnitude and direction of the magnetic field at distance Z along the Z-axis from the loop? So like somewhere out here, for example. Let's actually just go ahead and redraw this. And so say this is the Z direction. How do we find the magnitude and direction of the magnetic field at distance Z out here? So we have our current flowing like that. Let's say 5 minutes, and then we'll talk about this one. So what would be the magnitude and direction of the magnetic field out here? So, how could we actually go ahead and find our magnetic field out here? Or first of all, do we know how we could find the direction of the magnetic field first? I'll give you a hint. It's using everyone's favorite rule. Yep, exactly. We're going to use a right-hand rule here. Does anyone know what right-hand rule we're going to use to find the direction of the magnetic field?
You're doing the current, right? Okay. So, don't you curl your fingers in the direction of current? Right? 1 second. So if your R is like this, would your magnetic field be pointing down?
And how did you get that?
So I put my middle finger as like an arbitrary point, like Z on the Z-axis, for example,
Mm-hmm.
and I know the direction of the movement of current, which is going into the page. All right. So my thumb would give me my magnetic field, in other words.
Well, unfortunately, you're wrong.
Oh.
But so we have all these different directions of current, right? We have, so if you were to say you think it's going straight downward, well, we would have like this component, the magnetic field from this component going into the page. This is like into the page, sort of, and then this is out of the page.
Mm-hmm.
So
Wait. If that's the case, if you curl your finger towards current, that means your magnetic field's going to the left.
exactly, yeah.
All right.
We curl.
I was overthinking it.
Yeah. So we curl our fingers in the direction of the current, and we find the magnetic field inside our loop, and within the radius of our loop is going to be going this direction to the left through the loop. And so, does anyone know how we would actually go ahead and find the magnitude of this magnetic field? Don't feel too bad if you don't know how to. But
Don't you have to like draw lines, like make a triangle, I guess? Like you pick a point and then you draw like a line to the circle, or because your current's making a circle, and then you
Mhm.
can find the magnitude of your magnetic field.
So you're
Like
saying
that, yeah.
so.
And you do one for the bottom too.
Mm-hmm. And we're going to combine that idea with what Alana said, the BS law, the Biot-Savart law. We can actually use that to find our total magnetic field. But
So since you know your y cancels out, it'd just be all in the x direction.
or in this case, the z direction.
Yeah, then the z direction. My bad. Well,
Yeah.
in this case, yeah, the z direction.
Yeah. So we know that the total magnetic field is going to be in the z direction, and we have to somehow use the Biot-Savart law. Now, we have to, unfortunately, we can't use our simplified version of the Biot-Savart law. So, technically, this problem does go a bit further than what you guys are going to end up seeing for this class. Because, it was in the curriculum in past semesters, but I guess this is one of the things they decided to drop. But essentially, we can use our general form of the BS law to derive this. And so how would we actually go ahead and do that? Well, let's go ahead, and if we remember, we can pull up our general form of the BS law, where we have B is equal to mu naught I over 4 pi. And then we're going to somehow integrate over all of our current, which is our loop. Does anyone know what sort of integral, like what sort of coordinates that integral is going to be in?
It goes from negative pi to over 2 to positive pi over 2.
So are you saying it's like polar coordinates or
Yeah, I think it's
cylindrical
polar
coordinates? Yeah. We're going to do some sort of a, and it's actually not from negative pi over 2 to positive pi over 2. It's going to be, we're going to go all the way around the loop, right?
Oh,
So we could say negative pi to positive pi, or I prefer the basic 0 to 2 pi. So we're going to have some sort of integral from 0 to 2 pi. We have our ds length, which is, our infinitesimal distance along any part, and the cross product of that with our radius distance r, right? And so that's ds times r, and does anyone know what this radius r would be? If this here is z, and let's say this radius here is r, cross product of ds and r, this radius r would just be the square root of r big R squared plus z squared, right? And we have that r on the bottom. So r squared plus z squared, which, by the way, that's a constant that can come out. And then we have this cross product with ds cross r hat, which is the radial direction. And we have ds times r hat, which we'll just say that's r hat is the radial direction, so it's just the unit vector of 1. And then we have the sine of the angle between them, right? And what's that sine of the angle? Well, we know it's going to be something like this. I'm trying to visualize it. And S is going to be, do we know how to find what ds is? I don't know if you guys are totally familiar with cylindrical coordinates.
1 second. Bro, think. Wait. When ds just become a sine? Oh no, you already did that. Never mind. When? I'm trying to think. Wouldn't ds be like z hat or something? Or no?
Well, let's take this first of all. S is our total circumference, right?
Mm-hmm.
And so our total, what's the total circumference of a circle? 2 pi r, or in this case, we'll call it the total angle around the circle theta times r, right?
So the total angle would be 360 degrees.
Yeah, and that's how we get our 2 pi r. We have the radius around it times the radius. And this is actually big R here. And so then ds, what are we integrating with respect to?
You're integrating with respect to two. I mean, my bad. With respect to the circumference.
Yeah, we're integrating around the entire circumference.
So in other words, you're trying to find the area. Am I thinking wrong? No, you're not. Not taking the derivative of it. You're integrating it. So you're doing the opposite.
Yep. So are we integrating with respect to theta, or with respect to r?
You're integrating it with respect of r.
Are we? Isn't r a constant radius? We're going around from 0 to 2 pi, right?
So it'd be with respect to theta then.
Yeah. So ds would be r d theta. And we would actually, this theta is different than this sine theta here. This is just, we can sort of ignore that, and that becomes part of our it essentially becomes part of, it actually ends up canceling out with when we integrate all the way around. So essentially, this is a bit further than what you guys are actually taking a look at in this class, but our total magnetic field would actually end up being mu naught I naught over 2 times our big radius r squared over r squared plus z squared to the 3/2. I realized about 5 minutes before the session that this is something that was actually removed from the curriculum this semester, but figured it'd still be interesting to at least take a look at real quick and sort of understand some of the calculus that sort of can be applied in physics. So if we have our magnetic field and we know the direction straight to the left, what would be the direction and magnitude of the force acting on an electron that's located at z is equal to plus 6 centimeters and with a velocity of plus 20 kilometers per second in the z direction? So the electron's here and it's moving to the right. What would be our force acting on the electron? You guys 2 minutes to think about it. Would there be no force? I think you might be onto something, Elena. Why would there be no force? Researchers can't contort your hand. Be parallel with the magnetic field. Exactly. Or in this case, anti-parallel. Because our magnetic field's to the left and the electron's moving to the right. But then it has a negative charge, so it ends up, becoming whatever. But basically, it's parallel with the magnetic field. And the cross product, what's the force of a charge? What's the force on a charge in a magnetic field? Remember, for a current, it's IL cross B. For a single charge, it's what? Go back to last week. Yep, exactly. QV cross B. Which, once again, V cross B is V times B times the sine of the angle. And in this case, the angle is 180 degrees. It's anti-parallel. Sine of 180 is 0. Force goes away. Boom. And so now, what if instead our electron were to move in the x direction? What would be the force acting on the electron if the electron were moving in the x direction? Let's take like 3 minutes, then we'll talk about it. So we have our magnetic field, we have the electron, we have its location, and we have its velocity. Let's actually take 5 minutes, and then we'll talk about it. Let's take about 2 more minutes, then we'll talk about it. All right. So, how do we actually go ahead and find the magnitude and direction of the force if the velocity of the electron is in the x direction? First of all, what direction would the force be in? We apply our right-hand rule, right? With our velocity going to the right, we know our magnetic field is in the negative z direction. Point our finger in the direction of the velocity. Curl our middle finger in the direction of the magnetic field. And our force on the electron is in what direction? Downward. But our right-hand rule, our thumb should be pointing upward, right? What's going on?
Isn't it because it's the opposite? So like in a proton, it would be upward, but
Yep.
since it's an electron, it had to be the opposite.
Yep,
of it.
exactly. Negative charge, opposite force. So we know that our force on the electron is going to be downward in the negative y direction. And so now that we know the direction, let's just go ahead and calculate the magnitude. So we know the force is QV cross B. And so we know that that can simplify to Q times V times B times the sine of theta, right? What's our angle theta between the velocity and the magnetic field? Magnetic field is in the negative z direction. Our velocity is in the positive x direction. That's an angle of 90 degrees, right? So sine of theta is just 1. So we just have QVB. And so then if we want to go ahead and actually plug in our magnetic field, we have QV mu naught I naught over 2 times r squared over r squared plus c squared to the 3/2. Let's plug it all in. What's the charge of an electron? What's the elementary charge of an electron? Does the number 1.6 times 10 to the something sound familiar? 10 to the what?
-12.
Negative 19. Zach's got it.
Oh, okay.
1.6 times 10 to the minus 19 coulombs. We're going to keep everything in SI units. And our velocity, which we said was 20 kilometers per second. That's 20,000 meters per second. Times our magnetic field, which is mu naught, which is 4 pi. I'm just going to do 2 pi times 10 to the minus 7 because we have the mu naught over 2. Times our current I naught, which is 3 amps. Times our radius, r squared. Our radius is 3 centimeters. 0.03 squared divided by our radius, once again squared, 0.03 squared, plus z squared. Our location along the z-axis is 6 centimeters, so 0.06 squared to the 3/2. Plug it all in. We get a force on the electron of about 1.8 times 10 to the negative 20 newtons. That's a really, really small force. But it's still going to accelerate the electron a lot, right? Because what's the mass of an electron? Like, what order of magnitude is the mass of an electron on? It's like 10 to the minus 30, right?
Isn't the molecular scale? It's really small.
Yeah. It's like 10 to the minus 30. I think it's 9.1 times 10 to the minus 31 or something. So about 10 to the minus 30. So even though this force is really, really small, the mass of the electron is even smaller. And it's still essentially going to, in the blink of an eye, go yoom straight downward. All right, does anyone have any questions about this?
No.
All right. In that case, thanks guys for coming. If anyone hasn't filled out the attendance form, if you do that, that'd be greatly appreciated. Hope this helped out a little bit and didn't confuse more than it helped. So I feel like that happens sometimes. But hopefully this and yesterday's session, if anyone missed it, you can check it out in the Session VODs channel. Hopefully they help you out for the quizzes tomorrow.
Have a nice rest of your day.
Yep. You too. Have a nice day, guys.